the next topic, alkenes. As far as the promo exam is concerned, the sections on isomerism and cis-trans, in particular cis-trans isomerism for this covered in this lecture is still relevant. Okay. However, the fact that most of the material is not covered in the promo is not an excuse not to pay attention. Okay? Because alkenes, there are a lot of important reactions that you will need to know. For alkenes, there are only two reactions: combustion and free radical substitution. Okay? Alkenes are far more reactive. Okay? So, we are going to cover the structure, physical and chemical properties, preparations, reactions. Alkenes have two main types of reactions. There will be addition reactions when the double bond is broken, and there will be oxidation. Okay, you will need to learn the mechanism of addition, and then you will need to learn your favorite topic, identification test, because it comes from your favorite part of your practical, qualitative analysis, of which I'm sure you remember every single thing from year 3. Okay? Now, alkenes are basically I pause while there are very many very important people in the lecture carry on their conversation. Okay? Now, alkenes, there may be many terms that you are less familiar with. So, saturated hydrocarbon, unsaturated hydrocarbon. Okay, these terms you must know the meaning of. Saturated usually means that there are only single bonds. Unsaturated implies there are double or triple bonds present. Okay, so alkenes have at least one carbon-carbon double bond. Okay, the general formula is CnH2n, and this is isomeric with cycloalkanes, where there's a ring. Okay, so there are cyclobutane, cyclopentane. Okay, the simplest alkene will be ethene. Okay, so there are two carbons. Now, when we deal with organic chemistry, knowing the hybridization of the carbons is important. Okay, because it will help you to understand what is happening. So for ethene, it is sp2 hybridized. Alright? Then there will be this trigonal planar. Okay, so the molecule where there will be 3 hybrid orbitals and 1 unhybridized p orbital. Okay? So the molecule is planar. There will be 1 sigma bond formed between the 2 carbon. The second bond is a pi bond. So the double carbon-carbon double bond is made up of 1 sigma bond and 1 pi bond. Okay? The pi electron cloud lies above and below the plane. Okay, I'm going to do something a bit crude, as in unsophisticated, not problem. Okay? Because I want you to be able to do this during exam. Okay? So, the arrangement of this is your hybrid orbitals are going to be something like that. Okay? So, imagine a Mercedes-Benz symbol. You know the tree, the star? So, that is the trigonal planar arrangement to be like that. So, these are the hybrid orbitals. Okay? The p orbital will be perpendicular to this, to the plane. That's what I need you to understand. So these three hybrid orbitals are in the same plane. The p orbital is perpendicular to that. That's why they say the pi electron cloud lies above and below the plane of the molecule. Okay? Okay? So, the unhybridized p orbital, okay, will form the pi bond. So, now, let's look at hybridization a bit more closely. You have for sp2, now recall for ethene, you need 3 hybrid orbitals. 1 to form with the other carbon, 2 to form with the hydrogen atoms. So you need a total of 3. Okay? So you get the 3 hybrid orbitals by mixing 1 s orbital and 2 p orbitals. Now, because of this, they will sp2 orbitals have 1/3 s character, 2/3 p character. Okay? Knowing this thing about how much s character and p character it has is important later on because it affects the bond length. Okay? Now, sp2 hybridization, let's say if you start off with the carbon, this is the ground state of carbon, which means the arrangement in which the electrons have the lowest possible energy. Okay? Now, to get the hybridized orbital, it goes to the excited state, and then after that you combine the sp2, okay, 1s and 2p, and you get the sp2 hybrid orbitals, and then the p orbital, you have 1 unoccupied p orbital. Now, the arrangement of this as 1s, sp2, and then 2p in that sequence carries some information. It's telling you that the p orbital is still the one that is higher in energy. Okay, the hybrid orbitals are lower in energy. Okay? Okay. Now, why did this theory sort of come about? Now, if we say that for ethene, the carbon, the bonds, right, simply use the orbitals that are available, then we are actually limited to 2 single bonds and an empty orbital where maybe you can form a native bond. Okay? But you know that ethene has 2 single bonds and a double bond. So you cannot accommodate this. Okay? If you say that, okay, then you will excite one of the s electrons, the 2s electrons, to the 2p, then you have 4 singly occupied orbitals, then you have 4 single covalent bonds. But the problem with this is that, one, the bond lengths will not be the same. The one that forms with the s orbital will be shorter than the ones that form with the p orbitals. A second consideration is this. The bond angles will also not be correct, because the one that forms with the s orbital, it can come at any angle because the s orbital is a sphere. Whereas the ones that form with the p orbitals, then the bonds have to be at 90 degrees to each other, which you can do measurements and it shows you that the shape of the ethene molecule is not like that. Okay? So, this theory, the hybridization theory, can account for both the bond length and the shape of the ethene. Okay, so you have 3 equivalent sp2 orbitals and 1 unhybridized p orbital. Okay? So, one of the sp2 overlaps head-on with the other sp2 orbitals of the neighboring carbon atom, and therefore you get a sigma bond, a carbon-carbon sigma bond. Okay? The other 2 sp2 orbitals overlap head-on with the 1s of the hydrogen. Alright? Now, okay, I want you to take note of some things. The hybridized orbital always forms the sigma bond. Okay? Now, the hybridized orbital is also equivalent to a bond pair when you think back to your chemical bonding. So now we have 3 hybridized orbitals, and the shape, right, the bond angle is 180. Is the equivalent of having 3 bond pairs. You understand? Okay? The unhybridized p orbital overlaps sideways with the unhybridized p orbital of the other carbon atom, and then you form a pi bond. Okay, so to sum up, that double bond, you form a sigma bond using a hybridized sp2 orbital, and then the second bond of the double bond is a pi bond by the p orbital. Clear? I'm going to so much detail because you need to know this and you need to be able to draw it. Okay, you need to be able to draw this because it's specifically mentioned in the syllabus. Okay, so this diagram must know how to draw and label the bonds. Okay? Now, okay, I'm going to move on to a second example, but this is not your notes. It's not in your notes because you don't have to actually know it, but just for to illustrate this. We are going to talk about ethene, okay, where there's a carbon triple bond. The old name for this gas is acetylene, which you may have heard of because it's used in the blow torches when they want to cut metal or do welding. Okay, the oxyacetylene torch. Okay, so you have one S and one P orbital, so they have 50% S character, 50% P character. Okay, so from ground state, you get excited state, and then you have SP hybridization. I want you to take note of the two unhybridized p orbitals. Okay? This question is relevant to tutorial, not ALKENES tutorial, your intro to organic question 3 and 4. Okay? Because they have a structure there. Alright? So, you get this, two equivalent sp orbitals and two unhybridized 2p orbitals. Okay, when you form the CH2, one sp overlaps it on with the other sp orbital of the carbon atom, so you form a carbon-carbon sigma bond. Okay, the remaining sp orbital overlaps with the hydrogen atom, then you form a carbon-hydrogen bond. Okay, the two unhybridized p orbitals overlap sideways with the two unhybridized 2p orbitals of the neighboring carbon atom, forming two carbon-carbon sigma bonds. Two carbon-carbon pi bonds. Okay? Now, what is these 2p orbitals? What's the angle between them? 90 degrees, okay? In your tutorial question, you will see that instead of one carbon triple bond, they form actually two pi bonds. And my question about the bond angle is relevant to that, the tutorial question. Okay? Because you need to understand that to solve the question. Okay, then this horribly messy diagram need to understand, but I don't think you need to draw it. Okay? Can? Okay, so next, talking about the bond length between ethane and ethene. So, ethane hybridization is sp3, ethene is sp2. Okay, so the sp2 has a greater s character. Now, the s orbital is smaller in size. Okay, so therefore the overlap will be shorter than the sp3s overlap. Okay, therefore the bond length is shorter. Okay. Okay. To sum up for hybridization, this table is probably the most important thing. You need to know the information in this table. I will help you a little bit by telling you that when we talk about the electron pairs, we can be similar to bond pair. Okay? You're talking about the electron pairs. So when the two electron pairs is sp, so it's linear. Three electron pairs is trigonal planar, it's sp2. Four electron pairs is sp3, it's tetrahedral. Now, the hybrid orbitals are also the ones used to form the sigma bonds. Okay. The p orbitals, if available, either may not be used in bonding, or they will form the pi bond. Alright? Can? Okay, let's go. So we are done with hybridization. We can take a look at nomenclature, naming. Okay, so nomenclature of alkenes. I I think we've sort of covered. What's important is for you to know where the position of the double bonds are and how many double bonds there are. So the number tells you the position, the location of the double bond. The prefix, let's say di, tri, or that will tell you how many double bonds there are. Okay, so prefixes, substituents, okay, the stem and the suffix. Okay, now the stem, it should be the longest chain containing the carbon-carbon double bond. Okay, so the stem, you should number it to give the carbon-carbon double bond the lowest possible number. Alright? So, alkyl groups, halogens, amino acids, amino groups are named as substituents. Amino groups are NH2 groups. Bio students may be interested to know. Okay, the NH2 groups are amino groups. Okay, this thing, I want you to take a look. I want you to realize that the chlorine is labeled as carbon number 5. Okay? So it's 5 chloro. It's not 1 chloro. Okay? Because the carbon number 1 is the one for the alkene. You label carbon, the second carbon, 2 where the alkene is. Okay? The alkene takes priority. Okay? Now, the whole thing about naming can be quite tedious, quite confusing. Okay? The important thing is that you get yourself to a stage where if I give you the name, you can draw it. Okay? As long as you get there, to that stage, it's fine. Okay, so constitutional isomerism, same molecular formula, different structural formula. So here, what's the difference is the position of the chlorine. Alright? Okay, cis-trans isomerism. Now, this arises because of restricted rotation about the carbon-carbon double bond. In order to rotate about the carbon-carbon double bond, you actually need to break the pi bond, which will require quite a lot of energy. Okay? So, because of this, cis-trans isomerism arises on which side, the fact of whether which side of the double bond it is becomes important. Okay, so you have the groups on the same side of the double bond, it's called the cis-isomer. On opposite sides, it becomes a trans-isomer. Okay? Can? I think you have had some practice already. And this stuff, even though I'm sort of covering this again, because you would have been taught in your intro to organic, and therefore is examinable in promo. Okay? I will tell you when it's not examinable. I haven't reached there yet. Okay, so this one, don't do it. I think you all know that already. Okay, go to exercise 1. Seeing as how this is been asked already, it should take you about 60 seconds to do it, 10 seconds per structure. Go and do it now. Now take note that we didn't say displayed formula or skeletal, so you can draw whichever form you like. Okay, draw whatever is easiest for you. So it's easier to type this form. So that's why you often see this for the question didn't say draw skeletal or draw display, which means show the bond. So you can draw the condensed form, so you can imagine. Now, I noticed many of you are drawing the display. It's actually not necessary. You can actually, if you are used to it, drawing the skeletal formula is much faster. Okay, but anyway, it's just for practice because you have to know both anyway. Okay, so butene, cis-butene, trans-butene, and 2-methyl-propene. Okay? Yeah? This is the same as your tutorial question, in case you didn't realize. Are we done? And can I go on? People still coming? You got photos already? Yeah, go on. Okay. Okay, then you have cyclobutane and methyl cyclopropane. Okay, I want you to think a little bit about 5 and 6. What should be the hybridization there? And therefore, what is the bond angle associated with that hybridization? And then how is that related to the comment there that is less stable? And then I'll pick someone to answer. Just now the other LT, I picked all those people who I worked with during Pilusan. Okay? Anyone want to answer? Charmaine? What's the hybridization for 5 cyclobutane? sp3, good, correct. Sarah, if it's sp3, what's the bond angle? (109.5). Okay, then the rest of you, what's the bond angle here? It shows you as 90. Okay, so when it doesn't assume the normal bond angle, it's under strain. You need energy to force it to reach 90 degrees. Okay, therefore the compound will therefore be high in energy. Okay, it will be even higher in energy for the methyl cyclopropane because the bond angle there is 60 and it's supposed to be 109.5. So these compounds will be less stable because they are much higher in energy. Okay? If I'm not mistaken, they don't exist at room temperature. I'm not sure. Okay. Now, let's do a bit of revision in answering, looking at this. This diagram is connected to which topic? I heard somebody say good, thermochemistry. So what does the arrow include? I mean, what does the arrow refer to? What enthalpy change? What enthalpy change? So it's delta H combustion. Now, for delta H combustion, the end point is the same for all these three compounds. You both get CO2 and water. So, if the, okay, listen here, this is why I need you to understand. If the end is the same, then you burn the compound and they give you different values. It implies that the initial energy of the was different. That means the one that gives you a higher delta, more negative delta H combustion would have been higher in energy and therefore less stable. Okay? It's the same, you would have seen the same thing, similar sort of diagram when we talk about graphite and carbon. Graphite and diamond. Okay? Because when you actually go and burn diamond, it gives you a higher delta H combustion. And yes, there have been people who actually have burned diamond. Okay? Not the big ones, the smaller ones. Okay, so but1-ene, cis-but2-ene and trans-but2-ene, okay, they have different stability. Okay, the more substituted the alkene, the more stable the alkene. So you contrast with ethene, where only all are hydrogen, to the last one where all four have been substituted with alkyl groups. Okay? So the ethene is taken as the least stable and the stability increases as substitution increases. Okay, so look at this, is probably easier to understand. Okay, so you have the least stable, and then as you replace each hydrogen with an R group. R group, alkyl group means a carbon. Okay, think of an alkane with one of the hydrogens taken away and then you stick it onto the other compound. Okay? Now, when we look at, for example, cis and trans isomers, if you might think that being isomers, they would have the same stability, but there is a slight difference between the cis and the trans. Okay, I want you to look at the slide. If I were to just ask you, which one do you think looks more crowded? Which one do you see? Okay, good. Because that's actually what the whole thing is about. Where you have big groups, like the bulky group on the same side of the double bond, there is crowding. The term that we use is steric hindrance. Okay, when there is steric hindrance, it means it leads to the compound being less stable, because you can think of it as there is sort of a repulsion. Okay, but you don't need to go into great detail about explaining this. You say steric hindrance will be fine. Okay? Okay, so physical properties. Now, this will be connected with your chem bonding. Now, alkenes are hydrocarbons, so they are non-polar. Okay, so the boiling point, melting point increases with the number of carbon atoms. The intermolecular ID becomes increasingly strong. Straight chain alkenes have a higher boiling point than their branch isomers. think about piece of paper, we fold it, into a linear shape, right? There's a certain amount of the contact area, something like that. Okay? You go and crush it and make it into a spherical shape. The contact area actually decreases significantly. Okay? So this is the idea that we are talking about. Alright? Okay, so alkenes non-polar, so insoluble in water. They are very soluble in non-polar solvents like benzene. Okay, this one I think is quite straightforward. Okay, this one is slightly different. Need to pay a bit more attention. Now, if you have a cis compound, for example, this, and compare to the trans compound, the overall dipole moment for the cis compound is going to be higher. Okay? So this one will be FPD-PD. For the trans compound, the dipole moment actually cancels off. Okay? So what you have is you'll be held by ID. Okay? So this is something that you need to consider if they ask you to explain. Alright? They can ask you either they give you the boiling point and they ask you to explain, or they can ask you to predict which will have a higher boiling point. Alright? Okay? Okay? Okay. Melting point, on the other hand, is the reverse. Because melting point, we don't teach you the entire theory about all the factors about what affects melting point. Melting point, there's another factor, important factor that we don't tell you about, which is the arrangement of the particles in the solid. And this is called the packing. And it has quite a significant effect. Okay? So, the cis-isomer has a lower symmetry. Okay, so it doesn't pack as well as compared to the trans-isomer. Because of that, therefore, the intermolecular, it will have less significant, less extensive intermolecular forces. And so, it will require less energy to melt it. Okay? Okay? Okay, let's go on to talk about alkenes preparation, industrial preparation. Okay, some general knowledge questions. Just now, the last person I picked on was Sarah. Sarah, want to name somebody? No. Charmaine, you want to name anybody for me to ask a question? Don't think of my class. I think that Judy want to volunteer. She's just so happy. Where's my favorite student, Melson? Where's Melson? Skip Some today got video. I said it on video, so Melson. May I ask, is there anything that you have due for PW like the previous time? You didn't come to school today, or you came? Wait a minute, I don't see the other chairperson either. Oh, the other chairperson. Where's Nelson? Was he in school this morning? Silence means consent, right? Okay, never mind. Okay, Jeanette, anyway, since Nelson is not here. What kind of organic compounds are found in crude oil? Okay, correct. What kind of hydrocarbons? Hey, I'm asking this. I don't consider it part of chemistry, but it's to me, it's simply knowledge any educated person should have. I bet if I ask your GP tutor, she will know. Okay, now they are mostly alkanes. There will be significant amounts of aromatics. Okay, there will be some alkenes. Okay, now why do we need to do cracking of crude oil? Because why do we need to do cracking of crude oil? Good. It's because of the different crude oil is a mixture of different chain lengths. There is less demand for the long chain compounds because they are like heavy oils. There are things like that you spread the road and the, the tar and all that. Okay, things like petrol, okay, will be, let's say, aviation fuel are shorter in length, so they do cracking to get more of these things. Now, when you do cracking, you get alkanes, alkenes, hydrogen. Where do we use the hydrogen? This is you have covered in your syllabus. Okay? Any idea, any guess? What? Good, very good. Formation of ammonia, Haber process. Okay? Now, why do I tell you this? Because there was a time when the price of oil went up, and therefore, after that, the price of fertilizer went up, and therefore, the price of food went up. And it was an econs case study. Okay, so it will be done at high temperature with a catalyst or without. Using a catalyst will lower the temperature. Now, take note. Hello. If we ask, okay, there's someone in a red sweater who's very happy. Okay, if we ask you for reactions, do not, can we say you want to prepare in the lab, do not give an industrial method. Okay? The lab method that you can use will be using concentrated sulfuric acid, heat, or you can use alumina and heat. Now, when we talk about reagents and conditions, please, when we do organic chem, just give us the conditions as are stated in the notes. Don't add on stuff, don't subtract stuff. Okay? Should you write the state symbol for the sulfuric acid? What's the state symbol for concentrated sulfuric acid? Liquid, yes. L, not aqueous. So if we don't give it to you, don't go and write it in case you made a mistake, unless you know very well. Okay? Now, the sulfuric acid here is to absorb the water. Okay? Okay, so I will stop here and I'll continue for